In our last class, we discussed about 8051 instruction set. We started with the hardware manual, which is the document that I already uploaded, which is Atmel 8051 Microcontrollers hardware manual. And we discussed briefly that this manual has two parts. So the first part is more important to this syllabus. The second part is also important, but we may not need to that extent of detail. So section 1 is something that you all must consider very carefully, which is the 8051 instruction set. So instruction sets is actually representing different types of commands or instructions which are understandable by the microcontroller 8051 series. So that could be any microcontroller within 8051 series. Okay, so in the instruction set, we had seen different addressing modes in the last class, and prior to that, we also discussed about the program status word, PSW. So program status word is one of the registers, it's one of the special function registers in 8051 architecture. And this program status word refers to different bits in this particular register. So we discussed this, and in the last class we mainly discussed about different addressing modes like direct addressing mode, indirect addressing mode, register instructions addressing mode, register specific instructions addressing mode, immediate constants addressing mode, and indexed addressing mode. So these are the different types, mainly 6 types that are available in 8051 microcontrollers. So addressing modes are basically representing different ways to express the value of the data, or where exactly we are putting the data, and the mechanism to find that out through an addressing scheme is called an addressing mode. So addressing mode is nothing but you are pointing out data somewhere in the memory or register or anywhere within your microcomputer system, and how you are actually addressing or expressing the addresses in your instructions, like directly or indirectly or immediately or through some registers or through some special registers, which are actually this register instruction and register specific instructions are pretty similar to each other, and then indexed addressing schemes. So I hope some of you must have gone through this document, and whoever haven't, I recommend them to go through the first section, as I said in the previous class. So there are different types of instructions. So we have covered different types of addressing modes, but all these instructions that are available in 8051 are complex instructions. Basically, 8051 belongs to CISC category, that is complex instruction set computing. In complex basically instruction sets, so that means each instruction may have several variants, and you have to remember those variants through practice. So it looks like this list is quite long because there are so many instructions in this microcontroller. But if you start practicing and writing codes by your own, you'll automatically get to remember the instructions very easily with time. So let's look at this arithmetic instructions, which is the first category expressed in this, given in this document. In arithmetic means basically we will have to do some sort of arithmetic calculations. So inside the microcontroller, and this instructions basically refers to simple addition, subtraction, and some variant of the addition, subtraction. Also, it offers multiplication and division. So we'll quickly review the types of the instructions. Now look at this table. First of all, before diving to the first instruction, which looks very obvious like addition, let's look at the heading of this table, which is important actually. So for subsequent understanding of all the instructions in a general format. So mnemonic is the actual representation of the instruction. So what exactly a particular instruction is doing. So that's a mnemonic. So mnemonic is a term which is used to represent the purpose of the instruction, something like add, something like add C, sub B. So these are basically the main part of the instructions which actually represents the mnemonic. Now this byte or comma something, that part actually represents operand. So like this byte, add A, comma something in the bracket, or basically this some extra adjacent data along with the mnemonic is called an operand. So this is each mnemonic basically has an opcode associated with it. So there is a table later on that we'll see in detail. So each mnemonic represents the purpose of the instruction, and every mnemonic basically, whatever the purpose might be, is associated with an operational code. So that code basically, add A means some 8-bit number, 8-bit digital number. Add C, comma A means some another 8-bit numbers, which is unique in this entire instruction set. And then after that, add or subtract, so whatever adjacent data is called operand. Operand means it's a type of adjacent information given with the mnemonic. So opcode and operand combined together forms an instruction, complete instruction. Okay, so there is a typing mistake by Atmel over here, I guess. But it's not necessary that every instruction should have an operand. So every instruction must have a mnemonic, must have an opcode, but not necessarily every instruction will have an operand. Like there is no comma something in INC, in A instruction. That means there is no operand to this. So operand is actually implied within the mnemonic. That means there is a fixed operation that this guy is doing, and it doesn't require any additional information to be supplied. Okay, so having said that, we can go to the instructions one by one very quickly. I think it's very simple if you understand these basics like opcode, operand, and how mnemonic is related to opcode. So this is basically some basics. Okay, and another thing is the addressing mode that we studied, that given an instruction, so this is a complete instruction. Okay, add A comma some 8-bit number, for example. So that complete instruction may be used in different modes, right? In different addressing modes. That means direct, indirect, register, or immediate. So as you see, all four are given X. So X means basically it is supported. So that what is the meaning of this all four? How do you know that what is this byte? So in direct, we give the 8-bit address. Okay. In indirect, we give indirectly supply the address. We say that where the address is stored. And here in register addressing mode, so here one of the special function registers, or one of the registers in the banks, register banks, is having the address. And immediate means the address is also, so you give the immediate value. In that case, this is not an address, rather it will become a data under immediate addressing mode. So I'll repeat this for the first instruction again. So if you understand the definitions of this addressing modes, direct, indirect, register, and immediate, so that means, so this add A comma this 8-bit number can be used in 4 different ways. That means that further means that add A has 4 different opcodes. Okay, so that is an indirect meaning of looking at this thing, that there are 4 different opcode variants for this add A comma 8-bit number instruction. So in certain cases, you will see only 3 or 2 or 1 are supported later on. So that means it doesn't support those 4 modes. So rather it can support either 3 opcodes. So that means INC, comma, INC, no comma here, some 8-bit number, byte is 8-bit number, digital number. So that means there are 3 different opcode variants for this INC instruction. Okay, but for INC A instruction, there is only one single opcode because it's saying accumulator only. So there is no other direct, indirect, all those variants available. So this is the meaning of this particular table up to this 3rd column. Now the 4th column means execution time. in X1 mode. X1 basically crystal oscillator mode actually, or basically the standard normal operation mode, because you always need some sort of external clock signal or a crystal oscillator connected, as we had discussed in the previous classes. So assuming you are using a 12 megahertz oscillator or crystal frequency. So if 12 megahertz is the crystal frequency, then this add a comma 8-bit number will take certain number of bytes. Now look at this, there is nothing given over here, but in the second instruction, let's see, consider second first, then we'll come to the first one. So add C a comma 8-bit number is showing that under all these 4 different addressing modes, it is taking just 1 microsecond. That means it is going to take 12 clock cycles. Okay, so this add C a comma 8-bit number takes only 12 clock cycles. Now, if the clock's frequency is 12 megahertz, then this is 1 microsecond. If this clock frequency is 24 megahertz, for example, let's take an example, 24 megahertz, in this 1 microsecond will become just 50%, 500 microsecond, and accordingly you just use the crystal frequency. So take the reciprocal of the crystal frequency and multiply with either 12 or 24, wherever you find this 2, this is 24, then wherever you find this 4, multiply that with 40. So that means how many microseconds, I can ask you one question in the exam, that if I change this frequency to, let's say, some other value, then what is the time that it will take for certain instructions. That means you have to remember actually certain facts. So this part actually you have to remember to some extent, and sometimes if the problem is too big and complex, then I may provide you the number of clock cycles. From there you have to calculate this microsecond time. Okay, so this is basically the meaning of this chart or this table or similar tables in the instruction set for this microcontroller. And if you understand these basic concepts like mnemonic, opcode, operand, then what is the description or operation of the instruction, and then the addressing mode, as well as how to calculate the time for executing an instruction or to perform the complete instruction command, then you have to use this thing. So whatever crystal frequency, take a reciprocal, multiply into number of clock cycles for a given instruction. Now, if this is 1 over here, then it is 12 clock cycles, right? As per this. Okay, so I think it's pretty straightforward. Only thing you need to know these facts. Now, add a comma byte basically means, so this means add a comma direct address in addressing mode, for example, let's consider. So then in that case, this byte becomes an 8-bit address. Okay, so this byte becomes 8-bit address if it is direct basically instruction direct addressing mode. Now let's look at another simple one basically, which is the immediate addressing mode. So add a comma some 8-bit number. Now that 8-bit number is not an address, rather it's a data if it is immediate addressing mode. So that means I can give some 8-bit number over here in immediate addressing mode. So add a will have a certain opcode to represent that. And then what is the purpose of this instruction? So whatever the data was present in accumulator, that gets added with the 8-bit number, immediate number. I'm considering immediate addressing mode. So immediate number, and that number should also be 8-bit only. It cannot be 16 or any other. It can be less than 8 bits, but up to 8 bits it can take. So 8-bit number plus another 8-bit number originally present in accumulator gets added up, and then the result comes in accumulator again. So that means the old number in the accumulator, which was there for addition, that gets overwritten. So the old number is no longer available in the accumulator after this instruction, because it gets updated with the result. Now the accumulator gets a result of the addition of these two things. But in addition, which is not written in this chart, is that the program status word gets updated, whether you have a carry or not after this addition. So that gets updated in your carry flag. So carry flag is basically here CY. So this carry flag gets updated, auxiliary carry. So auxiliary carry basically takes the carry after 4th bit of addition. Okay, and this carry is after 8th bit of addition. So there are two carries, auxiliary and main carry. So auxiliary carry gets, so after 4th bit of addition, like accumulator and the 8-bit data must have 8-bit numbers each, right? So it will start from the right, digit by digit, it will start addition. And after 4th bit, if there is a carry, then AC flag gets updated with whether it is 0 or 1. And then it will keep on continuing with the addition. And after 8th byte, if the 9th byte is present, then it comes to carry. So that means auxiliary carry just copies the 5th byte of after addition. So we are taking two 8-bit numbers. So we'll start from the right, bit by bit addition. Then if you come towards the 4th bit, we may generate a 5th bit, which is a carry, or maybe 1, or carry maybe 0 after 4th bit addition, which is 5th bit result is coming to AC. So 5th bit of accumulator is same as AC. Okay, and then there is no 9th bit in accumulator. So that 9th bit of, if whatever carry is 0 or 1 after addition, comes to CY. Now through subsequent instruction, another instruction, we can actually read this CY equal to 1 or 0, AC equal to 1 or 0. Okay, so that is the meaning of this immediate addressing mode. Now let's look at indirect and register addressing mode. So let's quickly review, basically we just review the immediate thing first, because we have done add a comma some 8-bit number, right? So look at the definition of this addressing mode. The value of a constant can follow the opcode in program memory. Okay, so opcode was present for this add a. So here in this example, they are giving move, but we were considering add a, right? So the opcode is given over here, but immediately after that, so there is a number which is given. So it is given expressed in decimal for ease, but actually the microcontroller gets it in the form of a digital 8-bit number. Okay, so that 8-bit number basically could be specified directly over here. So that is the meaning of immediate. So for immediate addressing mode of instruction, we generally prefer to write this hash symbol. This is an assembler directive. It's like some syntax to say that the next number after this hash is a data value. And the moment you write hash, so the assembler will take the opcode for immediate addressing mode. Okay, so it will not go to other addressing mode. So this hash is actually indicating this immediate addressing mode, and this is called an assembler directive. This is basically a type of syntax. So it's a method to say that the next value is a 8-bit number. So so there are other 3 modes, right? We consider direct. So in direct, what I said, add a comma some 8-bit address is given over here. So there is no data, so you don't write that hash symbol. So let's look at the definition of direct addressing mode. So in direct addressing mode, the operand is specified by an 8-bit address field in the instruction. So that means add a comma 8-bit address is there, and the moment you don't write this hash, so the data will be automatically considered as the address basically value. So that means what do you mean by this 8-bit address? So this add a comma 8-bit address means, so 8-bit address is locating or pointing to some memory or register in either inside or outside the microcontroller. Typically inside, because 8-bit addressing is only present in the 128 bytes of RAM. So 8-bit address means basically, so it can only point within the inside of the RAM, but it's not necessary that that is always the case, but typically that is the case. So for this 8-bit address, so what is the meaning of this? So within, if this 8-bit address is pointing to the location in the RAM where the data is present. Okay, so add a comma some 8-bit number means, so there is a data somewhere in the RAM memory inside the microcontroller, and the address of that memory location is given in the instruction. So this instruction will take the value inside the RAM memory space given by, pointed by this 8-bit address, then take that value and then it will add to accumulator, and then the result of that addition comes to accumulator. Basically, the purpose is the same, but what we are putting, either directly we are putting in immediate data, direct 8-bit data, or direct addressing mode. Basically, that means, so we are directly writing the address of the RAM from where the data should come. Now let's look at this indirect and register addressing mode. So let's look at the definition. So that's how we should actually proceed for proper understanding. So in indirect addressing mode, the instruction specifies the register which contains the address of the operand. Okay, so now there is a little similarity between the indirect addressing mode and this register addressing mode. Later on we'll see that. Okay, so the address register for 8-bit addresses could be anywhere R0 or R1 of the selected register bank. See, so in indirect addressing mode, only R0 and R1 are the registers, okay, to be considered. You cannot consider R2 or R7, those kind of registers. Or in indirect addressing mode, the address could be more than, if basically if address is 8-bit, then it is only R0 and R1 are actually used, or basically or R1, because any one can be used. Obviously, you cannot use both of them together in this case. But if you need 16-bit address, then you have another option, which is data pointer. Okay, so data pointer is a 16-bit register. So let's consider. So that means in indirect, so there are two options which are possible. Okay, so one is either 8-bit address where sub options are R0 or R1, and another option is 16-bit address, which is DPTR. Okay, so 8-bit address means R0 R1, 16-bit indirect address means DPTR. So that means there is, look at the variants then. So in add a comma byte, see, this is a byte, you don't have that 16-bit option over here. So DPTR is not applicable. So in indirect addressing mode, for this instruction, you must have add a comma address at R0 or address at R1. So that is the meaning of this indirect address mode. And obviously, the moment you write that @ sign, like we write in the email, that in my email actually sudeepnag1 @ece.iitkgp.ac.in, right? @ symbol should be applied over here. So instead of hash, look at this thing. So this @ symbol should be applied over here if you are going for indirect addressing mode. So for immediate, I said that you need to have this hash. For direct addressing mode, it is written that nothing should be written before the number, and for indirect, you should write this @. Okay, now in the register addressing mode, now you have the access to what is the register addressing mode. So you can use all R0 to R7. So all 8 register from any one of the 4 banks. Okay, you have to select the bank first through previous instruction, one of the previous instructions, and then you go and use any one of this R0 to R7. So after you select a bank, so from that particular selected bank only, any one of these 8 registers will be considered. So in look at this thing. So add a comma R7. So if you directly write anything other than even you can write R0 over here. Okay, but @ means only R0 and R1. But if you don't write @, then R0 to R7, any one of those 8 registers can be applied over here. So that means based on what is there, so if you have a number here without any special symbol, it takes direct addressing mode. So that means the opcode for add a comma goes as a direct, so there will be one unique value. But add a comma, basically same thing, add a, but due to this special symbol, takes a different opcode. So likewise, so if you write here the register name or the hash, so there are 4 opcode options for this first instruction. So that means wherever you see this 4 basically applicability options applicability, so that means there are 4 variants of add c comma a. So there is also another 4 opcodes for sub bb comma a and so on. So that, but INC is having only 3 options of opcode. Yeah, tell me.
So in this case, we cannot have the DTPR, right?
No, because it is basically 8-bit address. Okay.
Okay.
Yeah. Because addition, see, the addition is only done with a 8-bit number, and see, the point is add a comma dptr. Okay, so let me think actually from my past code thing. Yeah, so the point is it is typically meant for 8-bit addresses, but there are different instructions that you will see for dptr application, right? Later on we'll see that. So how we'll do the addition. So in that case, if you want something from that 16-bit space, so you need to apply two-step process. Okay, so what is that process?
Correct. So when you do it on the edge and then you do it on the low, right? Like in two separate instructions type.
Obviously, you have to do that, but before that, you have to bring in the data from, let's say, from the main memory. So suppose you don't need a 16-bit number. Okay, I see one confusion over here. Don't think that DPTR, if the DPTR thing is coming, but although not in this instruction, DPTR is pointing to another 8-bit number only. Okay, so it is only pointing to another 8-bit number from the external memory space possible. Now, if you want that data from external memory space, you have to use two things. So before this add, you have to move the data. Something like move a comma some data, or move b comma some DPTR data. Actually, should address given in the DPTR should be given. So you have to bring in the data from the external memory by using DPTR, if you at all need to do that, and then keep it in one of the registers like R0 or R7 or A or B registers, and then you can do this addition by using this 8-bit addition number. So there is no DPTR option in this particular instruction. Okay, but if you need to use DPTR, use another instruction before this add instruction using DPTR. You bring that byte from the memory and then keep it somewhere within the microcontroller. Then you do this 8-bit addition. But with add a comma this byte instruction, you only have 4 possible options. So similarly, this add a comma byte ignores the carry flag in its addition process. Okay, whereas the second instruction is pretty similar. Only thing that it considers carry flag, CY flag, in your program status word. So carry flag in the program status was whatever it might be from the previous instruction or any previous basically operation that you might have done earlier before executing this instruction will be considered. So that means carry flag will be considered as one of the inputs. So this is a 2-step addition. So there are first it will do 8-bit plus 8-bit addition. So 8-bit result will be coming, and then you will be basically adding up with the older carry value and then update the carry accordingly. Okay, so look at this. In the PSW, I'll tell you one interesting thing. So you see one reserved flag. Okay, so you can ask that, are they wasting the space? Okay, but the answer is no. Why? It is reserved for internal operation of the microcontroller. It is not accessible to us as a programmer. Okay, we are just writing some code to make the microcontroller work in our own ways. So, but this particular bit PSW,1 is not available to us as a programmer. So we cannot read or write anything at this location, that is PSW data 1-bit location. Okay, this is data 0-bit location, 1, 2, 3, 4, and so on. So up to 7. CY is D7-bit, whereas this reserved is D1. So this reserved bit is actually stored, is used to store the intermediate number. Look at this. So if I add this A plus byte, some whichever addressing mode it might be, so it must be generating one carry. So where that carry is going? That's an intermediate carry. That carry is actually stored in that reserved bit because you need some space to store this carry, right? All other registers are utilized. All other bits of the register can be randomly utilized in your code. So where is this internal intermediate carry should be stored? It is stored in that reserve flag, and then you just take that reserved flag, which is used within the instruction by the microcontroller automatically. Okay, and then it takes that value and then adds up with the older carry which was there in the CY flag. So this is how actually they designed this. Otherwise, what they could have done, they could have instantiated another bit separately, and then they would have used it. So instead of doing that, they're making an optimum use. So given at that time, this was the state of the art. This was the state of the art design. So similarly, subtract with borrow is there. So there is no simple subtract over here in 8051. Although the older microcontrollers or microprocessors had SUB instructions, that is out of your concern. But just consider that here in 8051, you always have SUBBA. In fact, you can think that if ADC add CAA comma byte is there, so what is the need of this? This looks like an additional thing, right? So only thing that here you actually save some complexity in the design, and it is the same basically instruction, except there are extra steps or extra clocks which are required over here for this carry. So in fact, you may not use at all this instruction. So that's my point. Okay, this instruction is itself is so sufficient, but in certain cases, only in few cases, you may not be doing only arithmetic operation, right? You may be doing some logical operation, or you can use this carry for some other purposes, not just as a result updation purpose. So for that, you can simplify by using this only add a instruction. But from the mathematical point of view, this instruction doesn't make much sense, because there might be carry which may be 0 initially, but we must consider that as our one of the data values. But in subtraction, basically in 8051, they have ignored this simple subtraction. Rather, they consider subtract with borrow, comma, byte from A. So look at this. In all these instructions, A are coming up. So that means accumulator is getting extra priority, you can see. So in most of the instructions, you will find in arithmetic or logical instructions, arithmetic instructions and logical instructions, the accumulator is having very high priority actually. So this is one of the most widely and commonly used register in the SFR list. So in some way, so it just takes the value, the previously stored value in accumulator, subtracts the given byte, given that byte is coming from any one of those 4 addressing modes, and then subtract the value of C, which is in carry flag, and then the final result of subtraction comes to accumulator. So that means the accumulator gets overwritten. So if you want to save this original data, then you have to copy that separately using another instruction, another previous instruction before this sub B instruction to any other register or the RAM locations. Then INCA. Now, simple addition and INC, actually this is all very similar actually. Only thing is that INCA increments the value of accumulated just by 1. The opposite of INC is DCA, which is decrement the value of accumulator by 1. So it's DCA means subtract by 1, and increment A means add by 1. So instead of using this full add like instruction, which takes 2 bytes of memory at least in certain addressing modes, obviously not in all. That's why to save memory space, they have come up with this kind of instruction which just takes 1 byte in the program memory. So look at this. So add a comma. This first instruction again. So what if, how many bytes in the program memory that we need from this instruction? We need 2 for this direct addressing mode instruction. Okay. But for the indirect addressing mode, we need 1 byte only. So only opcode itself is good enough, because there are 2 options of opcodes here, R0 or R1 over here. So in this case, you just need 1 byte of program memory. Whereas in the first case, direct addressing, we needed 2 bytes of memory. In the third case, also 1 byte of memory, because R7 is hard coded. So there are 8 possible opcodes actually present So not just 4. So within this category, there are 8 opcodes. Okay, so R0 will have one opcode with add A, R1 will have another opcode with add A, and so on. So there are 8 possible opcodes. The point is, each opcode is only 8-bit. So in program memory, you just need 1 byte space to store any one of those 8 opcodes here or any one of those 2 opcodes here. But in this direct addressing mode, you need 1 opcode to store the opcode for, one memory location for storing add A opcode, and you need another memory location to store 7x hex or whichever direct address, 8-bit address you are given. So 2 bytes of memory are required. So that means you have to do 2 times read operation along with program counter in address incrementing in between. Okay, same thing for immediate also. So you need 2 bytes. First byte, which is in the program memory, is for the opcode, and the second byte is for the immediate data. So certain instructions, see, look, just by one instruction, there are so many details, right? So how many bytes it is going to take on program memory, either 2 or 1 for all these categories. So in this first and the last category, direct and indirect, so there are two bytes each is required. But here, so there are 8 different opcode versions are available along with the operand. So you don't need an additional byte for the operand, because these are hard coded within the opcode. And there could be, what is the maximum number of opcode possible combinations? So it is 8-bit, right? 8-bit memory means 2 to the power 8, that is 256 types of opcode maximum is possible, and that should accumulate all the types of instructions. That is another way of looking at this design, that the microcontroller 8051 must have any number of instructions which is less than 256. Okay, and that is reality also. Okay, so increment A and increment byte is pretty similar. The only thing is that in byte, it is a 2-byte instruction. So you need opcode 1 byte for opcode of INC, and another for this byte thing, which is either direct, indirect, or register instructions. Now the point is, if it is indirect or register instruction, again you don't need this. You have to write in the instruction that INC R0 or INC R7, but the actual opcode is 8 bits. Okay, so you have to understand this fine lines actually that I am telling you, which are not written over here. So you have to actually dig in much longer documents to get this information, and these are the things that I have had done earlier. So that's why I can tell you that basically there are documents you can also read. So there are hundreds of pages of documents for this instruction set instead of just 24. Okay, so if you read those super detailed documents, you'll find these fine lines actually, that if it is INC some data bytes, let's say there is no immediate over here obviously, but there is a direct addressing mode. So some INC, some 8-bit number, which is an address in direct addressing mode, so it will take 2 bytes. But if it is indirect, like R0 @R0 or R1, so in that case you don't need that second byte in the program memory. You just need only 1 byte for the entire thing, INC @R1 or R0. Or if you go to registers R0 to R7, so no @ will be used in that case. So in that case also, there are basically 8 possible opcodes available here. Another thing, so if your address or anything, if your data is present in an external memory, external data memory, it's not program memory, because you are doing some operation with that external memory. So it must be RAM type of external memory, and which is a data type memory, not a program type. So program memory, we store the instructions and their operands. In data memory, we store generally data. Okay, in program memory we may have data, but we cannot change that data in the during operation. So here I am considering this thing is I'm writing it back to the memory. So if you look at the description, so it takes the value from DPTR. Now DPTR is a 16-bit register. DPTR has DPH and DPL. If you remember, data pointer high, data pointer low. DPH and DPL combined together forms DPTR, which is a 16-bit register. Now, this looks like from the description that 16-bit number plus 1-bit number, so that means 17-bit result is coming. Actually, no. So this is basically, it takes data from the DPTR. DPTR is a data pointer. So data pointer is basically data pointer is a register that points your data within the data memory, and it takes the data pointer value, and then it takes go to the address of that, and then it increments. Sorry, there is a slight change actually. Sorry, I'm actually slightly telling it this instruction. I am making slight mistake over here about that. I'll correct it. So in this instruction, basically, this is actually a 16-bit plus 1-bit addition. Okay, so if you find what I was saying, that there must be this kind of some extra symbol if it is present along with this kind of DPTR, or in bracket if you find DPTR, in that case it is indirect memory only. But here it is written actually, so thanks that I remembered it on time. So these are very fine lines actually you have to acquire in reality. So where DPTR is a 16-bit number, it's a register, DPH plus DPL. That 16-bit number you want to basically, let's say, point to the next location in the memory. So before pointing to the memory, you have to do this. Let's say you want to increment it by 1. Okay, so let's say I have a table in the memory, and that table is having some sort of song or image stored in the memory. So what I have to do, I have to read that memory one by one. So what I'll do, so while going to the next location, so unlike program counter, DPTR doesn't increment by 1. So program counter automatically goes to the next memory location by adding 1 to it with program counter. But with DPTR, data pointer, it doesn't automatically increase to the next location. Okay, so you have to do that through your code, and that's what is we are doing through this INC DPTR. It takes a 16-bit number within DPTR and adds up with the one. So it doesn't consider the carry flag. Okay, so it just takes the 16-bit number and then copies the added result with 1 inside the DPTR. And this is only possible if your result is up to, if the sum of the result is only 16-bit. If it is 17-bit carry is coming in this case, in that case, that will be ignored. That doesn't get updated in the carry flag. So this is basically something to read the tables, intermediate step, which is used for reading table. It is again 1-byte instruction. Now look at this. So there are two written over here. That means it takes 2 microseconds given clock is 12 megahertz. What is the meaning? Means that you have an ALU in the microcontroller, which is 8-bit. And the ALU is only doing 8-bit addition. So it will take DPH or DPL. So it will take DPL first, increase that with 1, and then it will merge with DPH basically. And then it will combine together. So it's a 2-step addition basically. You first consider DPL and your value to be added, and then you consider if there is a carry, intermediate carry after 8-bit. So that gets carried over to the DPH part, and then if there is any further carry after DPH, obviously it is ignored automatically. DPTR comes to 0. So let's say if on the highest possible value that DPTR can hold, 16-bit number, and if you add 1, so FF plus 1, so this is just 1-bit 1. Okay, so that means 1 and then 4 zeros. So the result of addition, but that first 1 is ignored because that's 17th bit, and all DPTR will get reset to 0000 at the result if the previous value of DPTR is if. Okay, so you can do this addition, very simple addition. So this is basically an intermediate step for incrementing DPTR for accessing data in between. So decrement we have discussed, it is -1 from the accumulator. Yeah, question.
So as you mentioned that inside add C and add mnemonic, you can have 2 modes, right? One is an 8-bit and the other is a 16-bit, depending on what mode we use for addressing.
Here
correct?
we have had only 8-bit addressing mode. Only these are all.
But the
So
instruction
whatever the,
itself will be 16-bit, right? Will be
yes,
16-bit round, right?
instruction will be 16-bit, two 8-bit
And
number.
what is the data bus width, program data bus?
Program data bus is also 8 bits.
So that means you must take at least 2 clock cycles to get the data from the flash,
Exactly.
right?
Exactly.
So
So
then
if you
how is
you
it
need,
that
it's not two
how
clock
is it that
cycles. I will clarify. You need two machine cycles. I'll come to that through timing diagram. So it's not just two clock cycles. It takes at least 6 clock cycles to take in those data, or 6 or 7 clock cycles. That means it takes two machine cycles, and each machine cycle consists of multiple clocks. Let's say 2 or 3 or 4 clocks. So for one machine cycle, it will take the opcode from the memory. Let's say it takes first machine cycle is typically 4 clocks, and then the second one, which is the data, typically takes 3 clock cycles in the next second machine cycle. So combined together, you need 7 clock cycles just to read. So out of 12 clock cycles, it takes 7 just to take your data to the microcontroller.
and this is because it's not pipelined also, right? Like it's like sequential.
It's not pipelining. So the strictly speaking, digital pipelining is something else, which is there in higher end processors, not over here. So
Okay.
it is, you can say, sequential execution, sequential
Okay.
operation. It's not
So then
pipelining. It's not the right.
my actual doubt was if it's an 8-bit instruction itself, like so then shouldn't you take lesser time? So shouldn't it have like one slash
Oh, okay.
something?
True, true, true. So if it is 8-bit instructions such as this one at the rate R0 variant, okay. So obviously you are saving 3 clock cycles. So in that's why. So you will see for these instructions. So there are different number of clocks that are practically used. But typically what they did at that time, so they wanted to make everything very predictable and uniform. So they actually reserved some time. So that's why you can see that here the timing is not written. That is the reason actually. Okay, so the timing is not written. It's not 1 microsecond because for this 4 types of instructions, it will take different basically cycles. For the indirect and register type of instructions, it takes 3 clock cycles. That means one machine cycle less than the other 2 types.
True, but it's the same for add with carry also, right?
Well, for add with carry, actually, they made it uniform. So, yeah, true. So that could be also the case with add with carry. But the point is, it is doing two-step addition also. So whatever extra thing that you must be saving, so that is actually getting added with this extra one-step addition because ALU is getting 2 times addition.
Okay, so basically you're saying that irrespective of what addressing I use, the amount of clock cycles it was is exactly the same for add with carry.
Is mostly the same for most of the instructions
Okay.
because for
Because generally, if it's
uniform,
not same, then it's written 1/2 or
right?
obliques are generally used. So,
Exactly, exactly. Oblique, or basically there must be minimum and maximum range for executing the instructions. So you'll find those kind of more optimized kind of approach in ARM and more modern microcontrollers. Okay, okay. So now next go to this decrement byte. So again, it is same as decrement A, but in this case, so this byte could be any byte actually given through direct, indirect, or register addressing modes. So the indirect means at the rate R0 and R1. Register means R0 to R7, any one of those 8 registers. So so decrement, you can decrement any byte either within the RAM memory space by using this direct addressing mode, or address specified by R0 and R1 as indicated by indirect addressing mode, or you can directly subtract byte from any one of the R0 to R7 directly. So you want to direct in register addressing mode, so you can take this byte as anywhere between R0 to R7. For indirect addressing mode, this is at the rate R0 or R1. That means it is pointing to some other memory, but address is in R0 or R1. And in the direct addressing mode, so you are giving the address of the anywhere within the RAM space, whether it is bit addressable or byte addressable. So you just take 8-bit number anywhere from the RAM space one, and then subtract that from one and put it back to the same original location. So that is the meaning of DC byte instruction. Okay, and now the multiplier, multiplication and division instructions are coming. So multiplication division instructions are very similar to add and subtract. Only thing is the operator is multiplication operation. So in this case it can do two 8-bit basically multiplication. It takes two 8-bit numbers, and these numbers are fixed. One in must be located within one in B and other one in the A registers. Okay, so these are the two 8-bit numbers to be multiplied, and the result of 8-bit multiplication is 16-bit number. Okay, in digital you can do the calculation, right? So if you need 16-bit space to store that number, and that's what I think you can understand from here. The most significant byte, so 16-bit number has two 8 split it into two 8 bits. So the most significant byte, like D15 to D8 part of the result, comes to B, and D7 to D0, basically the least significant byte of the result, goes to register A. Now you have the 16-bit number. Now you can transfer them one by one or separately to memory location or other location separately. Okay, so this multiplication instruction typically associated with some another previous instruction, which is move something to B, and then another instruction afterwards, that is take these two bytes separately and put it somewhere else in the memory location. So the multiplication instruction doesn't come alone. It comes with some predecessor, and afterwards also there are some post instructions are given after this instruction. Same thing for division. Yeah.
Sir, is there a comma between A and B? MUL A comma B.
It doesn't make sense. Basically, you can keep basically that comma, but there is only one option, so there is no other option. Okay, so it doesn't. So it is actually mul A comma B also you can write. So that is our representation. See, whatever you write under this mnemonic side, it is just for our understanding. It doesn't have any direct meaning for the microcontroller. Every instruction is associated with background opcode. So that opcode must be correct, whether you write comma or dot. So that doesn't basically make much sense. Okay, because mnemonic is just for us as human to understand and interpret the operation of the instructions. But opcode, which is in the background for this every mnemonic codes, that is the most unique and important thing for the microcontroller, because the opcode is getting decoded, not this MUL. So we don't say ASCII values for this. We only say the ASCII values until the assembler or compiler. So in the C compiler or assembler, so we only write this DC, add, mul, all those things. Okay, so it doesn't make any difference whether it is dot or comma or nothing. Similarly, div, division instruction, div av, you can basically take this integer, basically the quotient and the remainder part for these instructions. And so for the quotient part is basically gets stored in the accumulator. Okay, so A divided B, quotient part of the answer comes to the accumulator, and the remainder part comes to the B register. Okay. Another way of writing the same thing, quotient and remainder. So basically you can see the quotient comes to A and the remainder comes to B. So again, this is 8-bit. So if you want to do more basically longer digits, longer number of bits, you have to do or apply multiply and division in steps. And see the number of clock cycles. So it takes 12 into 4, that is 48 clock cycles. So basically, if the clock is 12 mega, it will take 4 microseconds. So it takes drastically different timing. And why it is so? because actually it takes care of some temporary registers. If you remember the block diagram, there are two temporary registers inside the microcontroller around the ALU. So those temporary registers are also utilized to store intermediate data, and then it applies multiple cycles back and forth between those temporary basically registers and the accumulator. So in order to calculate this, either this multiplication or division instructions. In modern microcontrollers, these are done in much more efficient way. So it doesn't take so much time. In the RISC processors, you don't need 48 clock cycles kind of thing. But anyways, nevertheless, 8051 makes that standard. So this was the first microcontroller ever which was able to do multiplication division. So in today's time, it may look so backdated and outdated kind of thing. So it's taking so much time, slow kind of microcontroller. But think of 1978 or so at that time. So this was the state of the art, the first ever microcontroller in the world which can do multiplication and division. So that kind of glory was there actually with these instructions, these two instructions, mainly these two instructions. While this was basically at that time, even I was not born. Obviously, you can see that kind of thing, the glory those people might have received from Intel. Okay. Then
one more question. So when you div AB, the 8 bits in B, they're what, like a fixed point number, or they're
these are all
integers
fixed
only?
point. No, these are all fixed point number. These are not. No, you mean fixed and floating point. So these are not.
No. Fixed though has to be there. But I'm saying, does it have a decimal point, or is it just integer?
No decimal point. No decimal point.
Okay.
So it should be an integer number. It must be an integer fixed point number. So there is no decimal point. Obviously, if you need decimal point, you have to go to floating point. And floating point multiplication and divisions are supported in digital signal processors, which are more advanced arithmetic processing unit actually exist over there with much more dedicated hardware multiplier. This is also a hardware multiplier which is activated by using the software, but this is not very efficient, I'll say. So the more efficient and dedicated hardware multipliers and accumulate unit, MAC units, are there in some modern microcontrollers and traditionally in digital signal processors, which is one of the variants of microcontrollers for doing number crunching kind of work. Then the last instruction in this category is DAA, is called decimal adjust accumulator. Okay, so DAA means decimal adjust accumulator. So what is the need of this instruction, of this decimal adjust? Decimal, see, while we do basically simple addition or basically subtraction in microcontroller, typically it is related to addition and subtraction, I'll say. We need to display that result in decimal numbers. Suppose I'll give you an example from the internet. I just pulled out something which is very relevant over here. So look at this example. They're doing addition of 38 and 45. So by a normal addition, we get 83 in decimal number, right? So we know basically this is a decimal, two-digit decimal number. But if you convert this 3 and 8 separately, 4 and 5 separately into binary, and then do the addition, so the addition result comes at 7D. Now, if someone tells you the result of 38 and 45 is 7D, so obviously we get confused. 38, 45 we are telling in decimal, and result is in hexadecimal. So it is actually, we have to convert that back to decimal number, obviously. But directly it is little hard to interpret this kind of numbers, and more so if there are more longer digits actually, or wider digits, or wider numbers, like 4-digit or 6-digit numbers or 8-digit numbers. So for that, so the microcontroller actually helps you to convert this 7D into decimal number, so without applying a longer code to it. So you can obviously apply your own code to convert this hexadecimal to decimal within the microcontroller, but that will take even more space and time for the microcontroller. So instead, the instruction DAA is given where it actually does a very simple manipulation. Okay, so it just takes, if the number is more than, basically if you find anything more than 15, basically, so that means if you get anything in the range of in the answer, if you get A to F, anything in the answer, in that case it simply adds 6 to it. Okay, so it's, if you add 6 to the result, so let's say you get this 0 1 1 1, which is 7, and D is 1 1 0 1, so you just take 7D and then add 0 1 1 0 to it, okay, to the least significant nibble, and as a result you will get a value which is 1000, which is equivalent to 8, and 0011, which is equivalent to 3. So DAA instruction helps us to convert a binary number into a binary coded decimal number. So BCD is one of the important codes which is used for display purpose or data transmission purpose. So at that time, so it was more popular. Today also we have much more complex and powerful processors to deal with. So DAA kind of instructions are just like that. We can execute in a flash of a time. Okay, so this DAA instruction, nothing but it helps to convert your binary result after addition or any other subtraction operation, typically, to a BCD number. Now the point is, there is a limitation here. You have to think that if your result is having third digit towards the left, then there is a problem. Okay, then if you have a carry beyond this, so then obviously you have a trouble. So because why it is so? Because by using BCD, so the maximum number could be, it is not 1111. Maximum number is only 9, 1001. Okay, 9 is the maximum number, and here also 1001, that is 9. So 99 should be the maximum value after the decimal sum. If it is the case, then only DAA is applicable. Okay, so you have to make sure that DAA should be applied if the result is less than equal to 99. Then only you can accommodate within 8 bits. If you have anything more than 99, like 100 or more, up to 256, obviously you don't have the leverage to, or you don't have the option to use this another 4 bytes or another 8 bytes, bits towards the left. So DAA is an 8-bit operation, only applicable to accumulator only. It doesn't operate on any other register. If you have data in any other register, bring it to accumulator first, then do addition, subtraction, or whatever, and then you apply DAA instruction. Obviously, you will get a BCD equivalent up to 99 is valid, and beyond 99, it is definitely not valid. So DAA is one of the commonly used instruction used in calculators, for example. So as I said, if you can do addition or subtraction, and then the result is this one. Obviously, in calculator, your results are more number of digits are there. So for that to happen, you need a code to handle those many digits. But at up to 8 bits, it is direct, just one instruction game for the microcontroller. And this DAA instruction is so common that today in all the microcontrollers, in all the advanced microcontrollers like A78 or even those all latest RISC-V or IRM variants, they all have these instructions even today. But obviously in those processors or microcontrollers, it operate on 16-bit numbers and 32-bit numbers. Okay, instead of just 8 in 8051. But again, this DAA instruction was not the first one to come in 8051. There are older processors like 8085 which got this instruction for the first time in 1976 or so. Okay, on 75, 76, that kind of time it came up. But multiplication division was the first instructions that came up with 8051. Okay, so you can read the descriptions. Now we'll go to the logical instructions. See, if you have a good understanding of the arithmetic instructions, logical instructions are again quite simple and easy to understand. You can see the addressing mode for many of the instructions, like as I said, direct, indirect, register, and immediate. So these are the four commonly used. So again, 2-byte variants of the instruction and 1-byte variant of the instructions are available, as we had seen with ADD and SUBB instructions earlier. Okay, so let's look at this. It is very simple thing actually. This logical instructions. So first one is the AND L. And A-N-L-A, comma, byte. So ANDing instruction, basically that means if both the bits are 1, then output is 1. If one of them is 0 or both of them are 0, then the output is 0. So all this instruction actually takes bit by bit. So what I mean that I just go to this DA example, but ignore this thing. Just come to this part, where we are having this 38 and 45 in binary. So what we are doing in this addition purpose, so the same thing is also done in logical instructions. So we are doing bit by bit addition, like 0 plus 1 is equal to 1. Okay, so that's why we write 1 over here. Then we come to the next bit, 0 plus 0, 0, and so on. So same thing for ANDing or ORing or any other logical operation, we take bit by bit and then do the addition. So 0 and 1 should be 0. Right. So similarly here, so all the 8 bits are done by using this ANL instructions. Okay, ANLA instruction. Look at the limitation. The limitation is basically here. A is written on the left, but if you look at the next instruction, ANL byte comma A, that means the result doesn't come to accumulator in the second instruction. The result comes to the byte. And look at the addressing mode. So if the byte is there, that means you must give second basically an operand, and now the operand doesn't come at the last, it comes somewhere in the middle. Okay, so this operand, obviously the way to write the mnemonic is this byte is coming in the middle, but in the actual program memory space we just have 2-byte one. So ANL dash comma A is having one opcode, and that dash is given in the next location in the memory, and that is the second byte for the program memory space. So this is a 16-bit space is required for storing this instruction. But here there could be 8-bit variant and 16-bit variant based on these 4 addressing modes that it is supporting. Okay, so here the first one, the result is coming to accumulator, and the second one, result is coming to the memory location whose address is given, so whose 8-bit address is given. Then ANL byte comma hash data. Okay, now this is another very interesting. So you are actually getting rid of accumulator in this third instruction in the logical category. ANL byte comma hash data. That means you're giving the immediate data. Hash means immediate 8-bit data, and then this byte is obviously is giving the address of the memory location, because it's a direct addressing mode instruction, and it is, you don't have any involvement of accumulator for this ANDing operation. Okay, but the data where this ANDing is happening, it is happening only in the arithmetic and logic unit. Okay, so you should remember by now the block diagram of 8051. You should remember the register names at least and their purposes. In brief, at least some of them that we have covered by now. So if you know these 2 things, like block diagram and some special function register names and their purposes, you should be able to understand what exactly I'm saying, because this byte could be anywhere in the RAM memory space, this byte anywhere in the special function register. So that's what I am trying to say over here, and in order to understand that, you have to correlate to those 2 facts that we already covered. Okay, Similar to AND, so there are three categories of OR. So if you understand these three categories of AND, so you just replace the sign with OR for the next three instruction. ORL A comma byte, again 4 addressing modes. ORL byte comma A, so which is the result is not going to accumulator, instead going to the memory location that is given in the form of address with the instruction. So that address is now operand of the instruction. So I'm telling so many things. So mnemonic, opcode, operand, address, data. So this, there are only fine differences. Sometimes both, any two names can refer to the same location. Sometimes they are different. Okay, so you have to understand these things a bit carefully. So every mnemonic means for human interpretation, we write something in our user-friendly way, but every mnemonic has its opcode in the background, and the total number of bytes. Sometimes mnemonics have operand, and sometimes mnemonic, that operand takes an extra memory space. Sometimes that operand may not take that extra memory space in the program memory. Okay, ORL byte comma hash data, that means you just ignore accumulator, do it anywhere else within the RAM or SFR space. Likewise, another three instructions, XRL. So XOR operation, this is XOR operation. So this is exclusive OR operation. You know exclusive OR operation. So if the inputs are dissimilar, the output is 1. If the inputs are similar, like 0, 0 and 1, 1, the output is 0. So XRL is having again three variants: XRL A comma byte, XRL byte comma A, XRL byte comma data. Okay, so same. So that means just by like that you have learned 9 instructions at a go, but only there are 3 operations here: AND, OR, and XOR. Now, where is NAND and where is NOR? Those are the universal gates. So you can ask this question. So NOR, see, the NAND and NOR operations are typically not given. Instead, you have given OR and complement. Okay, so complement is basically CLP instruction. We'll come to the CLR later. It is super simple. Let's look at this CPLA, CLPA. CLP is complement A, so that means it's a NOT gate operation. Okay, you take something in the accumulator, you can apply a NOT gate operation to all 8 bits simultaneously using the ALU, and then result comes to accumulator. So if you need a NAND operation, go for AND and then apply CLP. If you need a NOR operation, go for OR and then apply this CLP instruction. So now it might look like why 2 steps, why not 1 step? So obviously this is how those people have thought to make it generic, so you can have both AND and NAND as well as OR and NOR. So both were actually considered. So only penalty, you have to use 2 instructions for NAND and NOR operations. Okay. But in modern days, actually, in fact, NAND is still not present. If you look at even ARM instruction set, still the same analogy is valid. People actually go by the same design ideas, that if you need a NAND, do it in 2 steps, and let's make each of those steps much more efficient. Like here you can see ANL is taking 24 clock cycles, right? 12 megahertz at 2 microseconds. So 24 clock cycles. So why not in ARM-like processor, the same AND and complement are separate instructions, but the number of clocks are drastically different. So in ARM, we'll do this ending in 1 cycle. Actually, even if it takes data somewhere else from the memory, it will take 2 clock cycles, not such a long 48 clock cycles. Sorry, 24 clock cycles. Okay, so this is 24 clock cycles. So instead of 24, ARM will take 2 clock cycles, and instead of 12 clock cycles here, ARM will take 1 clock cycle. So that's how efficient it is. And go by higher speed, so obviously your total time for each of those instructions terribly comes down. So that's how the advancement of the microcontroller technology or embedded systems have evolved over several decades. along with the transistor shrinkage or scaling technologies. Now we have clear A instruction. So clear A is just resetting everything in the accumulator. So just don't care what is there, what was there earlier. Make every bit in the accumulator 0. So if you want to make every bit in the accumulator 1, so do it in the NAND NOR kind of operation. You first clear everything in the accumulator, and I want everything to be 1 in accumulator. So I just use CLPA, which will invert all these zeros to ones in accumulator. Now another set of simple instructions, which is rotate. So logical instructions are pretty straightforward, I'll say. So rotate accumulator A and rotate accumulator basically, or rotate left or rotate right accumulator. So RLA is rotate left accumulator, RRA is rotate right accumulator by 1 bit. What is the meaning of this rotate instruction? So let's look at this. It shifts every byte by 1 bit location. Let me find some, so something like this. Oh. I'll drink some water. Let me find that. Oh, okay. So look at this. Rotate left accumulator, RLA. So rotate left means basically it is, suppose you have some data in D0 position, you shift that to the next position in the left, that is D1 position, and then whatever was there over here earlier, you shift it over here and keep on doing the shifting one by one. So that means shift from 6th location to 7th, 5th to 6th, and so on towards the until you end up with all 8 bits. And then what will happen if you shift 6th position to 7th? The 7th one actually rotates back. It actually gets copied to 0th location. So it's like a circular rotation in the left direction. So you are just shifting every bit from the previous to the left left location, just which is next to each other, and the last bit gets copied to the first bit. So for rotate right, exactly RRA, it actually does the exactly opposite thing, but exactly the same thing, but in the right direction, in the opposite direction. So whatever was there in 0th location, it goes to the 7th location, and the 7th one comes to 6th, 6th one comes to 5th, 5th to 4th, and so on. Okay, so now look at this and look at this RLA and RRA and ask one question to yourself. While I am copying this, let's say 1th bit to 0th position, where exactly this thing is going? Because I haven't copied this 7th one, right? 7th to 6th. I've just started from here, let's say. So what is done? So again, this extra, which is basically shown in this feedback kind of thing, this path, there is a reserved flag in between, which is not shown. Okay. As a hardware designer, you must ask, where is that extra bit is going where I'm making this shifting operation? Okay, so every time you are shifting, you are actually going through one extra bit which is coming out of the loop and going back to the other end of the chain. But while going back, so it must be stored. Think of a digital thing. So while I'm picking up water from my bucket, I use my mug, right? So I take the mug, it's like a local buffer. Technically speaking, your mug is a local buffer which is holding a little bit of water from your bucket and then transferring it to another bucket, for example, or to the same bucket later on in some different way. So that local storage is that reserve bit for left and right rotation again. Okay, but there are instructions over here, as I said, RLC, rotate left through carry, and rotate right, RRC, rotate right through carry. So rotate right and rotate left, basically through carry means you also consider carry bit in this particular chain of rotation. Okay, in this particular path of rotation. So you can, for the rotate left with carry and accumulator, basically carry flag is placed towards the left of D7 bit of the basically of your accumulator, and same thing. So you can just draw it differently in rotate right with carry, but typically the location, whether you make it next to 0 or next to 7th bit, it is the same location, right? So it is in the loop, carry is in the loop. So rotate right with carry, so that means 0th bit goes to the carry bit, and then subsequently it rolls back. But while subsequently it rolls back, there is a reserved flag which was there in PSW itself. Okay, so that also works in the background. So as a programmer, we don't get to see that, but it actually, that's why it is reserved for this kind of operations. Okay, so this is how basically this rotate left and right instructions are used. Now, another question that I'm asking to all of you and myself: why do we need rotate? So what is the meaning of this? I can give you a very ordinary answer and more technical in-depth answer. So let's look at the ordinary answer first. Why do we need rotate left and right? Ordinary answer: I want to design a light for Diwali or Durga Puja kind of decoration. So what I'll do, I'll keep on arranging 1010 or some sort of patterns, 110 110, something in my accumulator. And then I'll rotate it after certain time using timer or some sort of delay, and then give it to the IO ports, and each IO port could be having a transistor driver, something like a common emitter driver, or and then it will be driving some sort of LEDs. Okay, so that is one way. This is a basically technically I'll say relevant but weaker example. This is a simple example for decorative lighting purposes. But more technically speaking, what if I want to multiply by 2 every number? So I just want to double without using multiply and division instruction. So now I'll go more basically computationally intensive answer or method, where I can use multiplication for doubling the number. Let's say I have certain number, 8-bit number, I want to double that number to basically into 2. And then I'll again double it into 4, into 8, that kind of thing. So I can use multiplication approach. Multiplication takes 48 clock cycles, but rotate takes only 12 clock cycles. Look at this, rotate instruction takes only 12 clock cycles. So it is, if you rotate left by 1 position, you are actually kind of adding basically you can initially look at this, you can initiate a carry as 0, for example. So let's say I, through another instruction, which we haven't covered that, through another instruction I can reset the carry flag, and then I apply rotate left along with carry accumulator. So what will happen, this 0 will come and sit over here, and this bits will get shifted towards left. So as a result, if there is no overflow, so let's say this bit is not 1, until that point we are getting a double value within the accumulator after 12 clock cycles. Just opposite, divided by 2. Same thing can be done using this rotate right with accumulator, carry with accumulator. But again, there are conditions. You have to reset the carry for this doubling action. Also make sure this bit, whatever is there in D7, 0, preferably 0. It may be 1. There is no restriction as such. But in that case, you have to consider carry as a number also, which is the 9th bit number, but preferably 0, such that whatever number you have elsewhere within the other bits will get doubled by 2 or gets doubled just in one instruction or two instructions, including initiating the carry flag, and or divide by 2. So that can be done using this thing. And again, obviously, again you have to do that same rotation operation. You have to make sure the carry is 0, otherwise it may cause some problem. So with caution, you can use this rotate and right and left instruction for certain doubling or divide by 2 kind of operations, if you want it in a time efficient manner, obviously with certain limitations that we discussed. And the last one is the swap A, which is swap nibbles in the accumulator. So it is again given over here. So swap nibble means nibble is just a 4-bit chunk of bits within the accumulator or within any register. So it will copy bits D3 to D0 and put it in the right hand side, in the left hand side, D7 to D4, and it will copy whatever was originally there in D7 to D4 and bring it to the D3 to D0. Basically exchange this 4 bits with another 4 bits within a given byte, and that byte is accumulated. So this is basically swap instructions. So swap instruction is basically used somewhere basically in the sense that you wanted to transfer some data. For example, you wanted to make a serial communication with certain coding, or basically if you want to scramble your numbers for basically encryption. So old day encryption could be done. Today's encryption technologies are much complex and efficient, at the same time computationally hungry also. But a simple kind of thing, you can scramble the numbers or basically just exchange the nibbles and send the number, and then for security purpose, you're automatically changing the parity. Without changing the parity, you can actually change the number and then do basically transfer of data. And another example of swap A is that suppose you have a single digit display. So you must have seen 7-segment display. Okay, so 7-segment display. Let's. So if you look at the 7-segment display, you have seen many of this kind of calculator-like digits, right? So the digit names are called A, B, C, D, E, F, G, and dot point DP. So this kind of display is actually driven in this way. So there are LEDs. There are different LEDs for each dot. There are LEDs, and this could be common anode in this case, and also opposite one is available. Common cathode is also available. So whichever any one of these two should be used, and then you can use current limiting resistors here. And this is common anode type of display. So if it is common cathode, then this terminal should be grounded. Just opposite, right? Just think of cathodes are tied to it. So anyways, now this switches could be transistor switches, and each transistor could be driven by the microcontroller's I/O port. Now it requires 7 LEDs to be controlled in order to lit up the basically proper segments. Let's say I want to write 1 into it, so I'll turn on B and C and turn off all other segments. Okay, so that will be 1. If I want to write 2, A, B, G, E, D. So think of 2 written over here. So that means F and C as well as DP should be off. So this is done in this way actually. So there is a chip called BCD to 7-segment display driver. So this chip is used in calculator-like displays where only numeric digits are required to be displayed. And suppose you have only 1 digit. So in that case, you have to feed 4-bit numbers. So these are the 4-bit inputs actually. So they have not used one of these, possibly, I don't know. But there are 4-bit input, which is a BCD input, and there are 7-bit output, which are driving the segments. So it's a type of decoder. It's called a BCD to 7-segment decoder. So you don't have that in syllabus, but it's very relevant how this microcontroller technology actually evolved. So these are the predecessors. These are the older technology based on which all this swapping action was came actually. So if you can actually send 7 instead of 8 bits, any 4 bits after DAA instruction, and then you can get those decimal number equivalent displays. Those digits are displayed over here. Okay, so that is basically the use of there's another use case of swap instruction. Okay, and you can see that it can be applied after any instruction, so there is no limitation. You can apply it to add, multiplication, division, etc. Look at these examples later on. So there are data registers, data instructions, which are which is the basically next type of instructions, which is again another very simple but very logically designed and quite useful instructions. So these are data transfer instructions, like move. Okay, so move is very commonly used. So typically we use move instructions, MOV, not not MOVE. Okay, this is MOV only. So move is a very common instruction used to initialize registers, used to initialize some memory locations or RAM location or special function registers. You will see very often we will use this move instructions for initialization purposes, or after the result is calculated, the accumulator or register B is having some result, we wanted to transfer the instruction to another location. So move is the choice. So these data transfer instructions are again of various types. So most common type is move. So the first 3 moves are pretty similar to AND kind of, or those kind of OR operation that we've seen, 3 variants. So move A comma source. Okay, so that means source, SRC is source. So this source could be either in direct at all 4 addressing modes: direct, indirect, registered, immediate addressing modes. So this source means where the data is present, and I want to transfer the data to accumulator. So always destination comma source. Move destination comma source. So the operation for this A comma source, move A comma source, is A is getting copied with the data in the source, and now the source can be pointed by either addressing the registers R0, R1, or R0, R1 data itself, or immediate value, or the 8-bit address of the memory location. Okay, so wherever is the data, 8-bit data, it will just get copied. Remember, data must always be 8-bit because a accumulator is 8-bit. So you cannot do a 16-bit copy to 8-bit register. You can do other way around. 8-bit copy you can have to 16-bit register. We'll see that. But 8-bit value must only be written to a 8-bit register. Opposite to the first one is move destination comma accumulator. That means whatever is there in accumulator, transfer it to some destination using any one of the 3 addressing modes. Now look at this, immediate addressing mode is absent, and logically it should not, it must be absent. Why it must be absent? Because I'm transferring the value inside accumulator. Okay, this is the value inside accumulator to some memory or SFR location. Immediate address means there is some hash data. So if you give move hash data comma A, it doesn't make sense. You are giving a data and you are telling, hey, accumulator content should be copied to a data. No, that is not feasible. You can only copy the value of accumulator to some memory or SFR. You cannot copy the data into data. That is not possible, right? So it's like it doesn't make sense. So that's why immediate is absent. So move source, move destination comma source. So this is without accumulator. You can take either any one of the SFRs or RAM to any one of the SFR or RAM as both source and destination. So you can immediately basically have all 4 addressing modes over here. So here basically the source. So what is this meaning of this immediate over here? Why this immediate is coming? It is coming because you can give the source as any immediate value. You cannot give destination as immediate value. You have to remember this. Okay. So destination cannot be an immediate value in move instructions. only source could be an immediate 8-bit value in the move instruction. Okay. Now the next instruction is more powerful, relatively powerful, which is a 16-bit category of instructions. Yeah, tell me.
So the move destination source is a 3-byte command, right?
Depends on the addressing mode. Okay, so depends on the addressing mode. Suppose if it is move immediate, basically kind of command for destination comma source, it should be 3 bytes, or it could be in direct also. So this move destination comma source is a quite powerful instruction. It gives so many combinations. I'll tell you some of the combinations. Okay, so let's say I want to move R0 comma some immediate data, hash data. So what I need basically, so I need 1 byte for R0 and move, and another byte for over. But it's, let's say I want to move some address in direct addressing mode. I can make a combination of this. Look at this. I can make a combination of this addressing modes. Good question actually. So move, let's say R6, comma, no, it's not R6. Let's say move some address in the RAM, comma, some data. So let's say move some anywhere in the RAM space address, that address I'm giving here, 8-bit address, and another hash data is given over here. So that means it will take 3 bytes. 1 byte for move opcode, another byte for 8-bit address where I want to store the data inside that address, and 8-bit value that I want to store inside that address. So that means what I'm doing, hash data means I'm making using of immediate addressing mode, and some address over here I'm making some feature of the direct addressing mode. So I'm actually combining direct and immediate together in this instruction. So this is an option, and another option could be move b comma r0. Look at this, move b comma r0. How many bytes are required? In that case, you require only 2 bytes, because move b basically I think I have to check this how many instructions, but typically there are variants over here that I wanted to mean, where
It might just be just 1 byte because
yes.
B and R0 can be hard coded inside.
Yeah, so let's say move r0 comma r1. So that could be 1 byte instruction, but we have to check it actually. I don't exactly remember because it's a very long combination of things which are possible. But as I'm saying that there could be 2 bytes and 3 byte variants of this instruction. Now let's go to the next instruction. So if I can actually refer, or you can also refer to the detailed manual. I'll share that with you also. From there you will get exactly the answer that you are asking for. Okay, but sometimes it is, as I said, I am also not a good memorizer of things. I only try to go by logic. Okay, so that is the best way to acquire a larger set of information. Okay, so move dptr hash data 16. So that is basically, so what is the meaning of this? So data pointer is written with 16-bit constant number, an immediate constant number. That means, so this is a 3-byte instruction. Yeah, that means move dptr is a opcode, you will find 1 byte and 16-bit number, so 2 8-bit chunks of data, which are acting as immediate data for initializing the data pointer. So let's say I want to initialize data pointer somewhere in the memory space, and then I'll use data pointer in some other way. So I'm initializing the data pointer. So this instruction is used to initialize data pointer. Okay, so then these instructions are very interesting. Push and pop. Just a minute, I'll take some water. Push source and pop destination. this is related to stack pointer. So I will give you a small slide about this, but I wanted to draw something. I don't have something to draw over here, where I can draw it very neatly. Maybe I have some slides, but I'll just explain to you. So this push and pop relates to data transfer to the stack or from the stack memory or stack pointer. So what is the stack pointer? Stack pointer is another register, 8-bit register in 8051, which points to somewhere in the memory, internal memory space. Okay, so one second, I will stop sharing. I'll open up the one of the slides that I shared with you, and then from there I will continue. Just give me a moment. I'm opening the slides. So I'm opening the 8051 slides. Okay, it's open. Look at this. In this case, so the register bank 1 is used as stack. Okay, so I said that at that point that we will come back to this later on. So remember, register 1, this 8 bytes in register bank is initialized as stack. Now we'll go to another diagram. Look at the stack pointer in the block diagram. Okay, stack pointer is a 8-bit register. This is one of the special function or special purpose register, which actually stores 8-bit numbers. It addresses somewhere in the RAM in the R1, bank 1 locations. So what is the meaning of this stack is very interesting. Suppose I am executing a program, and that program gets an interrupt. So let's say someone is saying that, okay, you help me to identify the key press in the keyboard. So the microcontroller is originally doing something else or waiting even. And then someone is pressing the key, it generates an interrupt. An interrupt, whether it is hardware or software, typically hardware, if it is keyboard, it will come as a request. Interrupt is a type of request. I'll tell you again with hardware perspective how it is done. It is actually done through one of the IO ports. Look at this INT 0 bar and INT 1 bar, P3.2 and 3.3. So these are the basically two external hardware interrupts. So if you configure as INT bar and 0 or 1, this pins goes as input. Okay, so whenever I apply logic 0, let's say I am using only INT 0 bar. So in that case, if I configure it as input, I have to configure it as an input. And then if I apply a logic 0 to it, let's say initially normal state, it should remain at logic 1. And when active state of interrupt, logic 0 should come. Now, when logic 0 is coming, a hardware interrupt is actually reaching the microcontroller's internal timing and control unit. So where exactly this INT thing is going? INT thing is going actually to the timing and control unit, mainly actually through the IO ports, obviously through the IO ports. It doesn't go directly. So through the it is multiplexed with port 3. So through the IO port, it actually instructs the timing and control. There is an interrupt. Now what it will do, timing and control will do two things. First, it will say the program counter where to go next. So it will make a jump to the sub program or subroutine, which is an auxiliary program for servicing the interrupt. Okay, so whenever an interrupt comes, the processor leaves the main program or stops or pauses the main program, and it goes to the sub program. And how it is done? It is done basically by updating the program counter. So program counter is actually pointing to a memory location where the execution is happening, where all the timing and control and other execution or the main code is running. Now, due to interrupt, timing and control stops the program counter and it requires the program counter to be updated. Now, interrupt has come, it has to give a service to the interrupt by going to the subroutine. Now, the subroutine is, the processor will execute the subroutine if the program counter is updated with the address, starting memory location address of the subroutine. So subroutine is basically another program which needs to be executed now. Now the old program, the original program, is located basically running somewhere in the middle, and that middle address is given in the program counter. Now you want to save the value of the program counter in the stack memory, which is in the random access memory. Okay, so stack memory is just a part of RAM which is used to store the return address. That means whatever was there in the program counter in the original program, the next address is the return address, and that next address is stored in the RAM. Now, where in the RAM it will be stored? That is pointed by the separate addressing action or the address register, you can say, which is a stack pointer. So program address register and stack pointer are they are similar. Stack pointer is an address register which keeps a track where in the RAM we should store the return memory location in the from the program space or program memory space. So essentially the program counter after interrupt gets incremented by 1 automatically. That result after incrementation thing is stored in the RAM, and where to store in the RAM, that is indicated by the stack pointer. Okay, so I repeat again, stack pointer is a type of address register which keeps a track of the return memory location, which is basically some address value in the program counter, the next memory location's address value. So it will keep in the RAM. Now, if I give push instruction, if I give this push source instruction, okay, so what it will do, it will actually serve basically this two-step process. It will increment stack pointer by 1. That means the stack pointer is originally initialized at 08. Sorry, the stack pointer is originally given as 07, and then it will increment by 1, that is 08. Okay, so this register location is stack location, but stack is originally initialized as 07, so it will increment by 1. So see, INC stack pointer, there is no instruction. If you remember in the logical and arithmetic chart so far that we covered, so INC stack pointer basically is not a given instruction. You can use this as a stack pointer, or basically, in fact, this is actually, you cannot use as a stack pointer directly. You have to do that indirectly at all if you need stack pointer. But INC byte is typically used for register A, B, R0, those other serial port register, timer register, data pointer register. So those kind of registers. Okay, so INC SP is basically is not allowed typically over here, and INC SP is a special kind of purpose. Sorry to make you scrolling. Okay, so you have to do this INC SP first, and then it does execute this kind of instruction, move @SP. Okay, again, @SP is not supported in standard instruction set, but within push, it actually purposefully performing at least two of these instructions. So which is move @sp from source. So source is what is the source? Source is the program counter. Okay, so this source could be basically a program counter, and then this program counter is having 16 bits of information, and program counter value should be stored in the stack pointer. So that means I'll again go to the slide. So you come to increase stack pointer by 1, stored 8-bit value in 08 location. Then if the data is 16-bit, again increment stack pointer by 1, which is not written in that document. Obviously for 16-bit you need 2 memory locations, and first location is stored, first 8-bit is stored in 08 location, and the second part of program counter, second part of 8-bit 16-bit value, which is the next 8-bit, stored in 09th location. So by using push, you are actually pushing the value of the source into this register bank. Okay, now you can initially stack pointer in a separate way, that in that case you can initially to rank any other banks. That is also possible, but after reset, this is your stack location. So stack location means it's a group of RAM locations where you store the return address before servicing a subroutine. Okay, before going to a subroutine and executing, it will store the return address. Now after servicing the subroutine, what will happen? After serving the subroutine, we apply pop instruction. So we apply pop destination instruction. So pop instruction basically does exactly opposite. It actually takes the uppermost value from the stack, which is called top of stack. Okay, so 09 is the top of stack if there is 16-bit number stored in it. So the top of stack is stored back to the half part of the destination, and then it will decrement by 1. That means 09 in the stack pointer becomes 08. Then it takes the other 8-bit, which basically this is first in last out methodology. Okay, first in last out. So that means whatever you stored first, you 8 was location inside 8 was location 8 was stored first, so you are taking it last. You take it back to the other part of the program counter. Then again it will decrement by 1, so stack pointer becomes 07. So that means original location. So if you give one push and do something in between, and then afterwards you apply one pop, so the original value of the stack pointer will be same. Now if you by mistake if you give 2 times pop, then the stack pointer will go inside bank 0, which is a mistake. Okay, then your program will start malfunctioning. So as a coder, as a developer, you have to keep a track how many push you are giving and how many pop you are giving, and from not just that, from where you are pushing, the sequence of pop should also be in that way, in the first in last out strategy. So that means if you give push program counter or push R0, so you can have pushing 8-bit number or 16-bit numbers. Okay, so these things are possible. So also same thing, push, let me finish. So push PC, let's say I'm giving, and push R0 I'm giving. So 2 instructions side by side, one after another. Then I have to give pop R0, then push PC. So that I give push PC, push R0, and I do some code in between. After that, pop R0, then push PC, pop PC. Okay, so 2 times push, 2 times pop. So first was PC, last pop should be also PC. Yeah, question.
So essentially there are 2 parts. One, that push pop is also used when you're doing for a subroutine, right?
Yes, I am talking in terms of subroutine also.
So
in
no,
also
not
like
just for your program counter, but also for other variables in where
yes.
if you want to
Exactly.
save the state of some register where you're doing that subroutine. So actually the memory map that you showed, if you could go back to that, switch the tab. So over here, it only shows 8 locations at stack, right? In your bank one.
Yeah.
So my question is, so this is basically very much dependent upon the manufacturer of the chip, where he decides to put the stack, right? From what
Not
limit to what
necessarily.
limit?
Not necessarily. It also depends on the programmer. Very intricate question, and I appreciate that. Your stack initialization of the stack pointer could be something like stack pointer is initialized at 07. That means everything in the stack you want it to be stored within this 8 bytes of registers within register bank 1. So that looks like it. But suppose I give more than 4 push instructions. So if I want to push PC 4 times, not any 16-bit push for 4 times, then all these 8 bits gets occupied. Now, if I give 5th push with another 16-bit or 8-bit location, it will automatically go and overwrite bank 2. So the stack pointer doesn't get reset afterwards. So there is no upper ceiling that register bank should be stacked register. So your stack can actually keep on growing in this, even in the bit addressable RAM also. So generally, we don't need that much push instructions, but technically, and there is no limitation in the microcontroller. So you can keep on pushing something and something, and it will keep on increasing. In that case, there is a chance that you may destroy some of the useful data in the
Got it. So the programmer, you must know whether set some limits before, so that you can see whether your stack limit has reached or something like that.
Exactly. So the programmer must have a link or some sort of track to make sure the stack is overflown or not. So this is basically stack overflow is one of the terms, technical terms, that stack, suppose you are defining this 8 bytes location for stack memory locations.
Right.
So it should not overflow elsewhere.
The second part was, so as you said, it will go into the bit addressable RAM, right? So this is generally off chip, like the registers we talk about are generally like the on chip thing, which are memory hierarchy wise much faster than the RAM, right? So the read write time and all those issues arise.
So we have another lecture from 10. Can we leave?
Okay, so let me take the attendance. Yeah, let me quickly take the attendance, and then you can leave. I'll answer the question. Okay, students who want to leave, they can actually leave now. I've taken the attendance, and if you have questions, just stay back. Okay, so please repeat the question. It was not clear to me.
Right. Basically, these banks we have, these are already there, right?
Your voice is interrupting.
The possible or the bit.
I cannot hear you properly. Somehow your voice is getting disturbed.
Am I audible now?
Yeah, better.
Right. What I was saying was that we are technically using a different kind of memory hardware registers as well as RAM, right?
Yeah.
So that means that your I/O speed operation, latency wise, will be different in register banks as well as in the bit addressable RAM. So while theoretically your stack can grow, my question is that is there a problem during implementation, right? If it does grow over there, then will the system be able to automatically handle it, or will there be some issues?
Okay, timing basically issues or timing mismatch. Okay, so see, the stack is typically defined inside the RAM of 8051 at least. So it's an 8-bit register. Obviously, it should be there somewhere within the 128 bytes space. So whether it can be in the scratchpad space or bit addressable or register space. So all these memories inside the microcontroller are having the same latency or same speed of access. So even if you go from bank 0 to bank 1, it doesn't make sense. Similarly, any one of the banks to bit addressable or scratchpad, also the latency is the same because it is a contiguous implementation of the memory locations. Only the names are different, only the access mechanisms are different, but the timing part within the microcontroller is same.
Okay.
Now, you can also ask me one question: what if the stack pointer is outside the chip? By using DPTR or some other way, we can do that also in the external memory space. In that case, the timing is automatically taken care of because the moment you are handling external memory, the timing specifications are different and that is handled automatically by the microcontroller. But you cannot have a combination. So now the limitation, you do not have a combination of some stack inside the microcontroller and some stack outside. So in that case, your code should keep track, otherwise the microcontroller won't take any responsibility for that. So if you have a large stack to be stored, obviously you go to external memory only. So relieve these banks. Okay, is that clear? Can you hear me?
Okay.
I cannot hear you, but
Yeah. Guys,
your voice is disrupted somehow today.
second.
I cannot hear you. Okay, I don't know why. Your internet must be a problem or my internet. You can write me an email actually, Anirudh. I cannot hear you today. I don't know why.
But no.